Hi, it's Kate, and this is the third and final video of week 13, the final week of Math 23. Okay, here we go. So exciting. Let's talk about line integrals. All right, so we're going, in order to compute a line integral, what we do is we're basically integrating a vector field along a curve. Well, what do we care about? The basic idea, I'm going to start down here because this makes a little bit more sense before we get into what we're doing, which is listed up here. The basic idea is we're going to take this curve, we're going to break it into a number of segments. We're going, for each piece, for each segment, we're going to see whether the vector field that this curve is sitting in points in the same direction as the curve or opposite the direction of the curve. So what we're doing is we're taking the dot product of the vector field with the direction of the curve. And then of course we sum that along all the segments of the curve. And if we take the number of segments and we take that limit as n goes to infinity, we no longer have this approximating sum, we have an integral that we can actually take. So how do we even find a way to describe the curve? Well, we parameterize the curve using a parameter t that runs from a to b. Usually, we're not going to be doing curves that are too crazy, like if we were doing the curve y equals x squared. Y equals x squared, how would we describe that in terms of a parameterization? Well, it's quite straightforward, right? We're actually already given how to describe one variable y in terms of the other x squared. So our parameterization, where our parameter is t, would just say, okay, x is my parameter, that's t, and then y is just equal to t squared. So a good thing to note, though, is that gamma itself does not point in the direction of the curve. Gamma itself points from the origin out to a point on the curve. And it's not until we calculate gamma prime, the derivative of the parameterization, that we actually have a vector that's moving in the direction of the curve. So when we're like, we want to dot the vectors in the vector field with the direction of the curve to see if it's pointing in the same direction or see if it's pointing in the opposite direction, it's not gamma of t that we care about, it's gamma prime. But of course, to get to gamma prime, we have to go through gamma anyway. So the idea is we parameterize this curve using the parameterization gamma. We then we find d gamma, or gamma prime, to specify the velocity or the direction of travel. And so when we go about setting up this line integral, right, we're taking the integral of the dot product between the vectors in the vector field and the direction of our curve. Most texts, I changed the notation here, I used to say ds, but most texts will describe space curves as like r, so I just changed it to dr. F dotted with dr here, this means that we're integrating along the curve C. Now, of course, we have described C in terms of a parameterization gamma. We need to put everything in terms of the parameterization. So whatever the parameterization says x equals, we plug that into the vector field. Whatever the parameterization says y equals, we plug that into wherever we see a y in the vector field. So we do F composed of gamma of t, and then we dot it with, well, dr, which is the direction of the path, because we've parameterized the path using gamma. We dot it with gamma prime of t, that vector. So this gives the dot product totally in terms of the parameterization. We then take the bounds of the parameter. What is the parameter equal to at the start of the path? What is the parameter equal to at the end of the path? Those are our bounds of integration. And we integrate that. That will give us our line integral. There's an excellent walkthrough in the R script with fun colors and lots of, this is in parameter space and this is in the original space, and it completely, I think, is really illustrative and very fun to play with. So one thing that we will talk about is that this line integral, it happens entirely in the parameter space. And in fact, regardless of what parameterization you choose to use for this particular curve, as long as you follow this recipe, the answer, the integral that you get, the actual number that it evaluates to, is independent of parameterization. And we're actually going to prove why that is next semester, because that's when we're going to be talking a ton about integration. And so let's talk a little bit more about some cool properties of vector fields. So one thing is that if you have a vector field f that has the property where if you take a line integral of f along a particular curve c, and it doesn't actually matter the path that you take between one endpoint and the other, all that matters are the actual endpoints, we call that a conservative vector field, where if you took the line integral of a vector field along that blue path and you took a line integral of the vector field along the red path, they would be the same thing. That's something that a conservative vector field would do. Gravitational fields and electrostatic fields are conservative. Magnetic fields in general are not, but sometimes there are some examples where they are. If you're taking 15B next semester, I know a lot of you are taking 16 and 15A, so that's something that definitely comes up. So what's interesting is that if f is conservative, its line integral around any closed curve is 0, because since its line integral depends only on its starting point and its ending point, and you're going around a closed curve, that means that its starting point and its ending point are the same thing. And so you end up subtracting the same two function values from each other, so it would be 0. That's an interesting property of conservative vector fields. A necessary condition for a field to be conservative is that the curl of the vector field happens to be 0. Very interesting. A necessary and sufficient condition for a field to be conservative is that it can be expressed as the gradient of some function. We call that the potential function. Now, if you have a conservative vector field, the way to find that potential function, whose gradient is our vector field, is to evaluate f dotted with dr along C, where C is a straight line path from the origin to some point x, and we basically just use the parameter t. It ranges from 0 at the origin to 1 at x. So there's our parameterization here. And we can use that to compute a potential function. We'll have a lot of examples of that on, I guess, Thursday is our sample problem day. And what's interesting is that if the curl of f does not equal 0, the answer you will get is complete nonsense. Like, it's completely impossible to compute since f is not itself conservative. So this won't spit out a nice answer for you unless you're dealing with a conservative vector field. This practice will only work for a conservative vector field. So we'll be toying around with that more on Thursday. But that concludes sort of all of our lecture previews. It's been a pleasure. My cats are here to say goodbye for the semester. We will be having a review session later, but as always, if you have any particular questions about this material, please let me know. Thanks again, guys. Bye.